Hello Stats class, this is lesson 6.1b, continuing with random variables. And I'll remind you that last week in 6.1a we learned how to find the expected value, which is also the mean of x. So this is the symbol that you use for expected value. And if you use the Greek letter mu, then you're talking about the mean, but they're really the same thing. Mean of a random variable. Remember, I like to abbreviate RV because I get lazy. And as we learned last week, it's the sum of all the x values times their probabilities, or in other words, the value of each possible thing that x could equal times its probability, plus another value times its probability, plus another, and so on. And I write it out thoroughly like that because sometimes people don't remember what this thing means. It just means add up a bunch of stuff. So we're multiplying and multiplying and multiplying and then adding them all together. So that's the review part. And then today, you might have guessed what we're moving on to. We did the mean, and now let's do the measure of spread, which is standard deviation. And remember, the standard deviation is the average or typical deviation from the mean. Or distance from a particular value to the mean. And we spent a lot of time on this in chapter 1. We learned how to find the standard deviation with the long formula, which I'll remind you of. It's called S, and it's the square root of a bunch of stuff. And what you do inside the square root is you add up all the x's minus the means squared, add them up, divide by n minus 1, and square root it. And that was all back in chapter 1, long time ago. This is the standard deviation of a sample from a population. But now with random variables, we're working with populations instead of samples. And the population formula is a little bit different. So remember I told you back in chapter 1 we divide by n minus 1 and it's a long story. I'm going to tell you a little more of that story today. We divide by n minus 1 because that's what we need to make this represent the population standard deviation well. And the math behind it is complicated and I'm not going to go there. But basically they tried dividing by n and it didn't give a very good estimator. And so then they tried n minus 1 and it worked better. And I could prove it if I had to, but not going there. What I want to tell you is that with a population, you divide by n instead of n minus 1, which kind of makes more sense. It's more of a traditional average. So we're going to talk about a slightly different formula. Not much different. And I purposely put the chapter 1 formula here so we could compare them. A slightly different formula that we use for a probability distribution or a random variable because it's based on a population. And so we're talking now about the standard deviation. Of a random variable. So we're talking about a variable that could have many possible values that all have their own probabilities, and that distribution is really the population of all possible values of that random variable. So instead of S, we're going to call it sigma because that's the Greek letter for S. It looks like that. It's kind of weird. And sigma x, or the standard deviation of x, I'll give you the formula and then I'll talk a little bit about how it relates to that formula. It's got some similarities that I hope you will notice. So I hope you notice that we are still doing x minus the mean of x. We're calling it mu now because it's a population mean instead of a sample mean. And then we're still squaring that. That's still the squared deviations and adding them all up. And then dividing, instead of dividing by n minus 1, we're technically dividing by n because that's what this p is. This p is the probability of that value happening. And remember, the probability came from the number of ways it could happen over n. The number of ways it could happen is the weighted average, which we talked about when we did this as a weighted average. But that divided by n thing is replacing the divided by n minus 1. So that's the main difference. We look at it a little bit differently when we're doing populations. So we're going to shift from using this formula for standard deviation to using this one. Your calculator can do both, so that's not a big deal, and I'll show you that probably not till the end. Well, maybe in the middle. I don't know. I'll show you that in a minute. But right now, let's use the formula once just to make sure we've got it. I think using the formula is actually good for your brain. So let's do 3 flips of a coin like we did in 6-1A, number of heads in 3 coin flips. And remember, we actually wrote out this probability distribution already, but I'm going to write it out again, much shorter than what I did in 6-1A. So you could have 0 heads or 1 head or 2 heads or 3 heads. And there was one way to get 0 heads, tail, 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 and nothing else out of 8 possible outcomes. We listed them all in the other notes if you need to look back at that, but there were 3 ways to get 1 head out of the 8. There were 3 ways to get 2 heads, and there was 1 way to get 3 heads. So I'm not going to do the details of that again because we did it in the last set of notes. But we also found that the mean of this, since it's symmetric, is right smack in the middle. The mean of x is 1.5. So I'm just going to remind you of that. And then we're going to go from there to find the standard deviation. So on the AP test, they love it if you write out this formula. I am going to write it out. Even though it's long, at least there's only 4 things, right? 4 things I have to add together, and I'm writing them all out with a big, long square root. If I'm lucky, I can fit it all in one line. If not, I'll go down to the next line. So here's what we do. We're going to do the first x value of 0 minus the mean of 1.5, square it, times its probability. Do that again for each row. And this is where I'm doing it purposely the long way because I think it's good for your brain, and also because if you do it, if you're trying to show work on the AP test and you don't understand what this summation thing means, you'll mess it up. So I want to make sure that you've seen it long at least once. So then we're going to do 1 minus 1.5. I got that from the second row of the table. X might be 1, and then it would be this far from the mean. Square it times its probability. Do that with the next 2. Now I'm going to take the 2 minus the 1.5 and square it and multiply by its probability. And then I'm going to take the 3 minus 1.5 and square it and times its probability. So I wanted you to see that that is basically what this formula means. By the way, maybe we should have a box or something around this formula because this is like the important part of what we're doing right now. So when you do that, you could type all of this in one big long thing in your calculator, or you could make the calculator do the shortcut, which I will show you in a minute. If you do all of this order of operations correct and all that, which means finish adding before you square root and all of that, you get 0.866. I'm going to shortcut it and say most of the time, most people don't actually type all this in their calculator. They write it out so they get full credit on the AP test, and then they pick up their calculator and make it do that. So I'll show you how to do that in a sec. But first, what this means is this is the average distance from x to 1.5, which is the mean. So let's see if that seems reasonable. 0 to 1.5 is 1.5, 1 to 1.5 is 0.5. So if you take the 0.5s and the 1.5s and you average them, you get 0.866. Let's just confirm that with the calculator, and I will show you. Basically, you kind of already know how to do this on the calculator, whether you realized it or not. So if you have a TI 83 or 4, this is how you do it. Stat calc. Oh, first I should put my stuff in a list. So first, stat edit, put your stuff in a list. I have all kinds of stuff in this list that I was doing for some other class. That's nice. So my list 1 is going to be my x's, which are 0, 1, 2, 3, easy. My y's are going to, or my list 2 is going to be the p's, which is the probabilities, and that would be the 1/8. Did you know you can just type 1/8 there and it'll convert it to a decimal for you? And then 3/8 and then, oops, I just did 3 over 3 instead of 3 over 8, 3 over 8 again, and 1 over 8 again. And then remember, if you do stat calc, one variable stats, you have to tell it to look at both lists. That's the only hard part. So 1, not an I. Stats. You have to tell it to look at list 1, which is your X's, and list 2, which is your P's, or technically they call it the frequency list. So your X's, which is your data, and your P's, which are the probabilities of those data. So when you do that, it calculates a whole bunch of stuff, including the mean. And notice here's the standard deviation, right there where you need it. And notice that they didn't put anything with S. They put it with sigma. Sigma is the one that we want. S is the one where you're dividing by n minus 1, and sigma is the one where you're dividing by n, which I had not told you before this. And notice what they think n is right now. The calculator thinks n is 1. Do you see why that happened? It's because the calculator is adding up this total of all the p's and using that as its sample size. And if it tries to do that and then divide by n minus 1, 1 minus 1 would be 0, and it can't do it, and therefore that's why this is blank. So one nice thing about a probability distribution is you don't have to think about which one of these is the right one to use, because that one's going to be blank. Now, if I instead went in and put in the 133H, then it doesn't know it's a population, and then it will calculate. In fact, it gets the wrong standard deviation and the wrong mean also. You know what? That's just totally wrong. Let's not look at that. So anyway, you want to put it in as probabilities so that it uses the probabilities to calculate instead of trying to do it out of 8 possible values. So anyway, that is how you do standard deviation by hand or by calculator. On the quiz, I'm going to ask you to write out at least part of this formula, like maybe the first 2 and then a dot, dot, dot would be fine, because on the AP test, that's what they expect. So that is the first half of today's lesson. And the second half is something we can do to, like an application of this. So this is how to calculate it for discrete, which is what we've just been doing. But then you can also use it for continuous, and that's what I want to talk about next. So this stuff that we just did is about discrete versus we're about to shift into continuous random variables. So let's think about discrete versus continuous one more time. Remember, discrete means that you have limited numbers of possible outcomes. You can't get the actual 1.5 heads in 3 coin flips is impossible, which is fine. We can have the mean be impossible, but anytime that you can't have the numbers in between, you would have a discrete variable, and anytime you can have the numbers in between, then it's a continuous variable. So let's think about discrete would be something like shoe size. No matter how weird your feet are, you cannot go to the store and buy a size 7.1. If your feet are just a little bit bigger than 7, you have to buy a 7.5. So you can have holes and you can have halves, and you can't have anything in between. And that's an example of a discrete random variable. I guess it would be halves with a V. Sorry, I spelled that weird. And then continuous is if you measure something so accurately that you can have all those decimals in between. So if you measure your foot length as say centimeters with decimals on it, it could be any decimal. And that means that we could stop thinking about individual values for that random variable if we're thinking about randomly choosing a person and measuring their foot. That means that this could turn into a normal curve. And actually foot lengths do, or foot lengths, I don't know. They do turn out to be a normal curve because we are measuring something that occurs in nature. So continuous, the most important type of continuous you need to know is the normal curve. And so we're going to review some chapter 2 for the second half of these notes. Normal curve is a very common type of continuous random variable, and it's actually the only type that we're going to learn this year. If you take more college math, you'll learn some other distributions that are continuous, but normal curves are what you have to know. So a continuous random variable in this class is mostly going to be a normal curve. Or I suppose it might look like the density curves we did in chapter 2 where it's a rectangle shape or something like that. I'm sticking with normal for now. So I want to do an example with normal curves and then we'll be done for today. So let's do, instead of foot lengths, because I don't have data on that, we're going to do the heights of women. Heights are another thing that often come out approximately normal. And if we were in class, I would make you guess. The mean height of women is 64 inches. I think this is US, and it might be different worldwide, but anyway. And the standard deviation of heights of women is 2.7 inches. And we're going to say our random variable is H, which is the random height of a randomly chosen woman. And of course, it's approximately normal. The heights of women are normally distributed, and so that would be given to you, and you could draw a normal curve, and you could find the mean, which is 64, and you could find the standard deviation, which is 2.7, so that's this piece right here, which means that this is 66.7, and then this would be 64 minus 2.7, which is 61.3. And you could fill in some more numbers if you wanted to. Just a reminder that the mean always goes here, and this is always the mean plus the standard deviation, and the mean minus the standard deviation, and you could keep going if you wanted, right? That should look familiar because we've done it before. And I want to remind you that we've actually done some stuff before that is coming back again in this chapter. So we're thinking of this as a random variable, but what we did in chapter 2 still works. If I want to know the probability of randomly choosing a woman and having her height be between 68 inches and 70 inches, there's the symbolic form of what I just said, so feel free to write down the words if you want. You do it the same way you did it in chapter 2. So I hope that this is not too long ago that you've forgotten it all, but you would find the z-scores for both of these. So you would take the 68 and convert it by doing 68 minus 64 divided by the standard deviation of 2.7. And this is a 70 z-score, 70 minus 64, and divided by the standard deviation. And that's how you get the two z-scores. No problem. This is 4 over 2.7, which is 1.48. And this is 6 over 2.7, which is 2.22. So these women are both taller than normal, taller than average. I shouldn't say normal because they are normal. They're in the normal curve somewhere. So we're looking from about right here to further over. We're finding this little area. So I hope that's familiar to you. We are going to find them. We could do it two ways. We could find them on table A and then subtract them. So on table A, I would need the positive side, and I would need to find 1.48. In case you forgot how to do that, you would do 1.4 and over to the column of 8s, which is 0.9036. Really what I'm doing is I'm finding the probability now that Z is between these two numbers. And when I looked up 1.48, I should have written down immediately 0.9306. And then when I look up 2.22, I get 0.9868. And I subtract those two numbers. .986. Did I do it wrong? I got different numbers last year, and that bothers me. I'm checking my work. 229868. I did it wrong last year. That's nice. Minus 0.9306. Oh, I could do this in my head if I wanted to, right? 62 and 5.0562. About 5% of women are between those two heights. Okay, fine. We've done that before. Remember, you could also do it on your calculator with a normal CDF command. Remember, that's in second vars in case you forgot all of everything. Or there are ways to do this on the computer also. There's that Geogebra Probability thing that I found, or there's a way in Desmos. Anyway, you'd put in your lower z value and your upper z value. And let's do it. Second vars, and then normal CDF, and the lower z is 1.48 and the upper z is 2.22. Leave the 0 and the 1 because that's for z-scores. And I got hopefully the same thing as before, 0.0562, which is, yeah, same thing, 5.62% of women are between 68 inches would be 5'8", so it's pretty tall for a woman, and 70 inches would be 5'10". All right, so that is actually totally review from chapter 2. We learned how to do it back in chapter 2, but it is the only continuous random variables you need to be able to do, so we're reviewing it in this chapter on random variables, and some of your homework will ask you to do things like this. If they tell you it's normal, you're doing this z-score and normal CDF thing that we have done before. All right, I'm going to stop there, and we'll go on to 6.2 in the next lesson.